Hello, everybody. We're still talking about the same case of molecular diffusion accompanied with first order reaction, homogeneous reaction. And we saw the concentration profile, and we want to get more out of this equation or this system by checking the flux. And this is actually an interesting thing. And if you want to get the flux, then we need to use the equation of the concentration. That Ca equals this form of the equation, and to get the flux, then we need to use the flux equation that says that flux equal negative d multiplied by dc by dz. So we need the dca by dz. So differentiating the function is going to be pretty easy because we only have here z in the cosine and in the sine. So we don't have multiplication of two functions or so. So it's going to be just differentiation of cosine, which is going to be sine, and of sine to be cosine. We don't change the signs, so it's going to be easy. So it's going to be the sine multiplied by the differentiation of the argument, which is the delta multiplied by the 1 over delta multiplied by the square root, and the same here. So this is what we're going to get. This is the differentiation of the argument. And this is the sine, which is the differentiation of cosine, and the same for cosine. For tangent is going to be the same because it's a constant, so I'm not going to do anything to the tangent. Then we can calculate or get the formula of the diffusion flux by using this function and using the dc, this formula of dc by dz in here, and then the equation would be like this. I just took the dca node over delta multiplied by the square root as a common factor. And this is the output. One of the things that would be of interest to us in the coming two slides is the flux at z equals 0. So if we substitute in this equation with z equals 0, then this sine would be 0. Sine of 0 is 0. Cosine of 0 is 1. So it's going to be negative 1 over tangent of the square root. And by combining everything together, we will find that it's going to be square root divided by tangent of the same square root multiplied by dc node over delta. What I'm gonna do now, and I think this is one of the interesting parts of this problem, is and again, this is not in the textbook, so I believe it's gonna be nice to share with you, is the flux profile. We have seen the flux profile in case of the heterogeneous reactions, and we saw that the reaction, even if it's heterogeneous, it affects the concentration profile and consequently the driving force, and so the flux is affected. So this is the same here, and here the impact would be even more obvious because the reaction is not taking place on the very far end of the diffusion distance. It's taking place simultaneously with diffusion. So in this case, you'd see that the flux is very, very, very much affected by the rate of reaction more than it is in case of heterogeneous reaction. And what we will see now is the flux as a function of z over delta, again from 0 to 1. But in this case, the flux is gonna be so it's like the same case, the same values of the square root. I'm gonna go from 0.01 all the way to 10,000, and we'll see how it will differ, how it will change. And this is what we will see. It looks kind of odd somehow, but this is very interesting if you check in more details. So let's see, this is the flux in the y-axis. This is in gram mole per centimeter square second. I forgot to put the units here. And this is the dimensionless distance on the x-axis from 0 to 1. And let me zoom in more just to make it more obvious for you. So I'm gonna go for the first case or the last case here, where we have k delta square over d equals 10,000, and this means that the reaction is very, very, very fast. So if this is the case, then we will see that it's starting at z equals 0 with the maximum value of the flux that we will have in the whole case, on all of the cases that we have, and it decreases really quickly. So you will have the flux here reducing by almost 10 times in very, very short distance, and each like small increment of the distance leads to a very huge decrease in the flux. So it goes from 10 power minus 4 all the way down to 10, almost 10 power minus 12 in less than 20% of the whole distance. And this makes a lot of sense, because you start here with very big flux, because you have a huge driving force compared to the rest of the cases. You have a very, very big change in the concentration in a very small distance, so you have a very big driving force. So at z equals 0, you have the maximum value of the flux. But then the component A is consumed very, very quickly. So the number of moles that you have are reduced significantly with a small change in the distance. And this is what we saw in the concentration profile. It was a very huge drop in the concentration with a small distance. So this is what we see here. The flux is reducing very, very quickly until it reaches a very, very small value. We can recall the concentration profile. We can go back and check it. That we saw, or we said that the concentration almost went to 0 in 0.08 percent, or 0.08 of z over delta, and this is what we saw from the graph. But what we see here is that the concentration, or there is a flux until 0.18, and this is because there were very, very little traces of A that led to this profile. And keep in mind that this is on a log scale of y, and the other plot was on a normal scale. So for the log scale, it can show you like very, very small values. If you plot the concentration profile on a log scale, you would see that there are very, very little traces in this distance here, which is this part, which correspond to a very, very small flux as well. The second plot here, which is the 1000, it makes a lot of sense as well, because you have lower driving force, so you'll have lower flux, and as in the first case, it keeps decreasing at like a slower rate, but still a fast rate, until it reaches the minimum value, or 0, at 10 power minus almost 13 or something, at z over delta equals 0.58, 0.57, something like this. This keeps, the trend keeps repeating. You start with lower flux, and the slope changes, and it takes longer distance until you reach a point. So this is the k delta square over d over 100, and then this is k delta square over d over of 10. And it keeps going until you reach a point where the reaction is not affecting at all. So this is for the last two plots here, for 0.01 and 0.1. You see they are almost overlapping. And you see the profile here is linear or homogeneous. So you have no change in the flux, so it's constant flux over the whole distance. And this makes a lot of sense, because as we said before in the concentration profile, that this is almost a pure molecular diffusion process, equimolar molecular diffusion process, without any reaction. So in this case, the flux is constant. So this is what we know from the equimolar counter diffusion, and that's why the value is here. So, and even if you plot more and more plots at smaller values of k delta square over d, it's going to give the exact same data. So it's going to be just overlapping over the same data. And this makes a lot of sense, and we will see in the next slide why. So before we go to the next slide, one of the parts of this plot which is going to be very, very relevant to the next slides is this part at z equals 0. So we saw that this is the flux at z equals 0, and this is at z equals 0 for different kd square over delta square over d. So these are the values, and you see it's getting starts with very large value, relatively, of course, at the very high values of k delta square over d, and it gets lower as we reduce the k delta square over d, and then it plateaus, and the flux is always constant at the low values of k delta square over d. So this is what we will study in more details. So we will compare the case of performing the process or the diffusion process in case of reaction and in case of no reaction. So if I don't have a reaction, then k equals 0. So I'll start with the differential equation. This is going to be very, very simple differential equation. We can solve directly. This is second derivative equals 0, so it's a linear relation, and between C and Z, of course. And then we can get the constants from the boundary conditions. We can substitute in the equation and get the form of CA as CA node multiplied by Y minus Z over delta, and this is the flux from this equation. So this is the flux in case of no reaction, and this is the flux that we got in case of a first order reaction, homogeneous first order reaction. So from these two shapes, and before we talk about the comparison, we could easily get this form even without going through the whole this whole derivation, because we know that at very small values of k delta square over d, which approach 0, then this tanh of x equals x. If x is very, very small, then tanh of x equals x. So this would be 1, and this is gonna end up to be the same shape. So anyways, if we compare the flux in case of reaction at z equals 0 with the flux in case of no reaction at z equals 0, it's gonna be the square root of this parameters divided by the tanh of this square root, and this is what we call Hatta number. So this is why we call it HA. HA is Hatta number, and Hatta number is a dimensionless number that takes into account the effect of chemical reaction on the diffusion, on molecular diffusion. So it's again, to put it right, the effect of the homogeneous first order reaction compared to no reaction in case of molecular diffusion. So if we plot the Hatta number for different values of k delta square over d, you would find that this is aligning well with the flux profile that we saw in the like a few slides back. So it starts with constant values, or almost a constant value here for small values up to 10 power minus 1. Which we saw already in the plot, the points that were overlapping, or the profiles that were overlapping for small values. We already used 10 power minus 1 and 10 power minus 2, so they all have the same Hatta number, or the same flux. It means that the flux is constant, and we can get this from the profile here, that the Hatta number is gonna be this term, which equals to 1 at very, very small values of x. So that's what we see here, that this is Hatta number equals 1. And for very large values of for large values of this k delta square over d, this tanh equals 1, because the profile of tanh looks like this. So it plateaus at larger values of x, at tanh x equals 1. So this is the value of Hatta number, which is gonna be so I think I plotted against the square root of k delta square over d. It's not the k delta square over d. This should be the square root. Anyway, so what we see here, that it's linear. So the square root is 10, so it's going to be 10. So it's exactly the same value, and we have this transition part between them. So we saw this increasing flux. So the increase in Hatta number means the flux is higher. So the increase in the flux as the k delta square over d increases. We have already saw this in the flux profile, and this is the transitional period where we'll have like an intermediate value between the Hatta number of 1 and Hatta number of the square root of k delta square over d. This is in the region where the comparable values of the flux and the diffusion coefficient, the diffusion coefficient and the rate constant. So this is what we can get out of this problem. In the next video, we will solve one more problem, and this is going to be the last thing that we cover in this chapter. And then we will go for chapter 25, which deals with the unsteady state molecular diffusion. So we will solve this next time, inshallah. So I'll see you then. Goodbye.